In today's video, we're going to investigate the relationships between the four quantities that completely describe any sample of a gas. Those quantities are pressure, which we looked at in the last video, volume, how much space it takes up, temperature, and how much is there, which we'll measure in moles because it's chemistry. These take the form of a number of what we call laws because they're empirical. In other words, we've observed these things happening. We've made these generalizations, and there don't seem to be any exceptions to them under a wide variety of circumstances, and so they've gained the reputation of being laws. The first one's called Boyle's law. Because these are empirical, I want to show you how this law is developed by actual observation. So we're going to look at a little movie here where an investigation is done into the relationship between volume and pressure, which is what Boyle's law describes, and then we'll summarize it.
Vacuum pump. You can see there are a couple of gauges on the top, and there's a hose that comes out of it, and that hose leads to this chamber here. It's not really a chamber right now, it's just a flat platen, just kind of a disc that's got a hole in the middle, and that hole connects to the tube that's outside. I have laying on there right now a syringe, and if you look at this syringe, you can tell that the volume that it's reading is about 4.3 milliliters. What I'm going to do next is put a lid on this chamber. Now the lids fit onto a rubber disc, so it makes a nice seal. And then I'm going to turn on the vacuum pump. In a little bit, I'm going to turn on the vacuum pump, and as I do, we'll watch the syringe change volume. As it's changing volume, I'll call out what the pressure gauge is reading from time to time. The gauge that I'm reading from is actually measuring vacuum. I'm going to call out millimeters of mercury vacuum, which is a way of saying millimeters of mercury less than atmospheric pressure, which we'll assume to be 760 millimeters of mercury. Here we go. $200. 300, 350, 400, 450, and 500. Let's make a table that has all the measurements from the movie. So I'm going to make a column for pressure, and I'm going to make a column for volume. Now we found that when the pressure was 0 vacuum, in other words 760 torrs, it's going to be pressure in torrs, the volume was 4.6 milliliters. When the pressure was 200 millimeters of vacuum, or 760 minus 200, that would be 560 torrs of pressure, the volume in the syringe was 5.6 milliliters. At negative 300 pressure, in other words 760 minus 300, or 460 torrs, the volume was 7. At minus 350, which would be 410, 710 minus 350 is 410 millimeters of mercury, or 410 torrs of pressure. The volume was 8.1. At minus 400, or 360 pressure, 9.0. At minus 450, which is 310 torrs of pressure, our volume was 10.5, and then the last measurement we made was a little uncertain. It was minus 500, which would put us at 260 torrs, 760 minus 500, and it looked like the volume was about 12.3, although we were off the scale, so it might be a little hard to tell. Now, here's what I'm going to do. I want to make a graph that puts pressure here and volume here and see what it looks like. I'll do this with the graphing calculator. First I need to put all this data into a list. Here in list 1, I'm going to put my pressures. So I'll just key those in. In list 2, I'm going to put the corresponding volumes. So now I have a set of volume and pressure data. I'm going to make a stat plot and just see what that looks like. I go second function, get my stat plots up here. I'll turn this first one on. I'll make sure it's a scatter plot. And on the x-axis I want to put pressure, and pressure was in list 1. And then on the y-axis I want volume. So second function 2 puts list 2 in there. I'm going to do a zoom number 9 to get a stat plot. And this is what it looks like. It doesn't look very much like a straight line. Let's do a regression analysis to be sure. The r squared value is 0.877, which isn't real good. So it indicates that it's not much of a straight line. But look at the graph. That also shows this is not much of a straight line. Those points don't line up very well on that straight line. So we don't have a linear relationship here. In fact, what we have is a graph that looks like that. Now, there are a bunch of different mathematical relationships that have that general shape. One of the ways that we can test and find out which one we have is by doing this. If we take the inverse of pressure and plot that on the x-axis, and on the y-axis put our other variable, volume, if we find that we have a straight line here, well then we know that the relationship that we have is what we call an inversely proportional relationship. Let's test and find out. So I'll go back to my stat editor. In list 3, I'm going to place the inverse of all the pressures. So I'll just hit L1 and hit its inverse, L1 to the minus 1. In other words, 1 over L1. So every pressure now has its inverse in list 3. Let's make a new stat plot. Go to my stat plot, plot number 1, and I still want a scatter diagram, but now I want my x-list not to be L1 but to be instead L3. So I'll hit second function 3 and change that, and then I'm going to do a zoom number 9 to take a look at my plot. Well, this looks a lot more like a straight line. Now when we do regression analysis, we get a much better r squared. That's indicating this really is a straight line relationship. The points lie right on the line.
Here's how we could state this in words. The volume of a sample of gas varies inversely with pressure. Now there are two conditions that have to be met for this to work. One is that you have to have a constant number of moles of gas. You have to have a constant quantity, so no leaky containers. And the second one is the temperature can't change. But if the temperature and the number of moles of gas are the same, then there's an inverse proportionality that relates volume to pressure. Here's how we'd write that in algebra symbols. We would say that volume is equal to a constant number times the inverse of pressure. That's what inverse proportionality means. Now, if you know what that K is, you can solve for pressure or volume at any time. But most of the time, it's not worth our trouble to find out what K is. So we have another way of dealing with this. And here's what it is. Imagine that you have one point on this curve where there's a pressure we'll call P1 and a volume we'll call V1 that correspond to that point. And then we can pick another point on the same curve. So here's P2 and here's V2 corresponding to point number 2. If I rearrange this equation, here's what I get. P times V is equal to a constant number. What that means is as long as you're on that curve, the product of pressure and volume is going to be the same. So at point number 1, you have pressure 1 times volume of 1, and that's equal to the constant. And at point number 2, you have pressure 2 times volume 2 that would be equal to that constant number. But since they're both equal to the same constant, here's what that means. P1 times V1 equals P2 times V2. This is what we call the two-point form of the law, and it's very useful for solving problems. Like say you had this one. A 1 liter bottle is sealed at the top of a mountain and it's brought down to sea level. Its volume there is 850 milliliters. If the pressure at sea level is 865 torrs, what was the pressure on top of the mountain? So we can modify Boyle's law for this situation by saying the pressure on the mountain times the volume on the mountain has to be equal to the pressure at sea level times the volume at sea level. So in this equation, what we're trying to find is pressure on the mountain. So we'll solve for that by dividing both sides by volume on the mountain. So pressure on mountain is pressure at sea level times volume at sea level divided by volume on the mountain. Pressure at sea level was 765 torrs. The volume at sea level is 850 milliliters, which I'm going to call 0.85 liters because my volume on the mountain is in liters and I want my units to match. Divided by the volume of the bottle on the mountain, which was 1.0 liters. So liters are going to drop out of this, and I will get pressure units, which is good because that's what I'm trying to find, of torrs. And the answer, which has two significant figures, is 650 torrs.
Here's an illustration of that from a vacation that I took once. These are my kids and I sitting at a tea house that's very near the top of a high mountain in the Canadian Rockies. And take a look at this water bottle. There's a little water in there, but I drank all this water and sealed it up so that there was some air in there, which is a gas. And that night, we took off on a drive, and we headed west, and we went to the coast with this water bottle sealed up in my backpack. Well, the next day we were in Vancouver. You can see here, this is my son standing there with the same water bottle in front of the North Vancouver Hotel. Vancouver is at sea level. It's right on the ocean, on the coast. And here's a close-up of the bottle. Look at what's happened to the bottle. The bottle has actually collapsed. Its volume has gone down because the pressure went up as we came down from a high mountain